Today we're going to look at volumes of solids of revolution using the washer method, but having it rotated around different horizontal and vertical lines, not just the X or Y axis. So I'm going to write that down here, not just X or Y axes. So let's just review when we do rotate about the X or Y axis, and then we'll generalize. So here we have a region R that's bounded by that square root function, the x-axis, and the line x equals 9. Set up an integral that will find the area in terms of x, the area in terms of y, and the volume of the solid when region R is rotated around the x-axis. To take a minute and try that yourselves. So first we sketch the region, y equals root x, the vertical line x equals 9. Notice that the intersection point here is 9, 3, and this is 0, 0. And so if we wanted to get the area of that region in terms of x, we use a vertical rectangle which spans the region. The top and the bottom hit the same functions. So it's just top minus bottom in terms of x from x equals 0 to x equals 9. If we use horizontal rectangles, we integrate with respect to y. So in that case, it's right minus left. The right function when we solve for x is 9. The left function when we solve for x is y squared. And the limits of integration would be from 0 to 3. If we rotate the region about the x-axis, around this axis, then we use a vertical rectangle, and when we rotate that, we see that we do get a disk. This is a washer with no inner radius. So to sum up the volumes of all these disks that slice through the solid, it would be top minus bottom squared, which is the radius of the disk. This is the radius, from 0 to 9, and there's a pi outside the integral. Now let's extend the problem to something else. Let's take the same region bounded by y equals root x, x equals 9, and the x-axis, and rotate it around horizontal lines that are not the x-axes, but parallel to them. In the first equation, we want to get the volume of the solid when we rotate the region about this horizontal line, y equals 3. So y equals 3 is this line right here. This is y equals 3. That's our axis of revolution. And remember, the axis of revolution always goes through the middle of our disk or washer. Okay, this one is y equals 5, which is a little bit above y equals 3. And that's y equals 5. And then the last one is y equals negative 2, which is below the region. And we're going around this way. So we are still going to use our vertical rectangle that we use for area and rotate that around. But these rectangles are a little bit different because now in D and E, we're rotating up, the region up. So this region here will be reflected this way. I guess something like that. We'll get a circular base this way, but this red rectangle will be reflected up, and we have a red rectangle here that will be reflected up. Notice that these would be our washers. Here it looks like it's a disk, but it's a tiny washer. It's a wide washer with a tiny inner circle. So we have washers going that way. Now the question is, how would we represent the integral to get the volume of this solid? Well, we have to think about this carefully. So for this integral, the pi still goes on the outside. The limits of integration, because in terms of x, will be 0 to 9. In fact, this is true for each one of these, because we're going to use a vertical rectangle that's going to be rotated around the line. Okay, we'll draw the washers in the other two, but let's discuss the inner and outer radii. Now, everything is relative to the x-axis. So think of it this way. The distance between the axis of revolution and the x-axis is 3 here. In the next one, it'll be 5. And in the next one, it's going to be 2. So we always consider the distance between the axis of revolution to the x-axis. This is important. We know that the distance from y equals the square root of x to the x-axis is the square root of x. So this distance, I'll put that in red, is the square root of x, right? At any x value, we could find that height by taking the square root of x. So the question now is, how can we represent the outer radius and the inner radius with respect to x? Well, we know that this distance is 3, right? And this distance is root x. So the inner radius would be 3 minus root x, which is the radius of the empty circle. So the second part would be 3 minus root x squared, because we have to square the inner radius. Oops. But we also have to subtract the outer radius. If you take a look at the outer radius of the washer is the distance from the axis of revolution to the x-axis, and that's always 3. And that's squared. So that is a little bit confusing, because the outer radius here, which is this distance, is always from the center of the washer to the x-axis, and that will always be 3. But the inner radius will vary depending on the radius of that hollow circle, and that will be 3 minus root x squared. And we put brackets around here, and we have dx. All right, let's look at the next one. When we rotate this red rectangle about the axis, we've got a hollow piece. Okay, this part is empty. So we'll have an empty piece here, but the rectangle would be rotated about here. So I'm just going to draw one washer, so we could identify the inner and outer radii. Okay. So I'll do this I'll do this in red again. So the distance from the function to the x-axis is still root x. Okay, this distance, this height is still root x. But the distance from the axis of revolution to the x-axis is 5. And now we would like to represent the outer radius, and the outer radius is the distance from the middle of the circle, middle of the washer, to the x-axis. This is the outer radius, and the inner radius is represented by the distance from the center of the washer to this piece. That's the little radius. So how can we represent that in terms of 5 and root x? Well, the outer radius will always be 5. I mean, if you look at it and compare the yellow segment to the green segment, that is always 5. So this would be 5 squared. I'll put it in green. That's the outer radius squared. Okay, this should be a square. I don't know why I put a cube. Okay. Minus, now the inner radius will vary depending on where the washer is. And that is 5 minus root x squared. And we put brackets around that, dx. All right, now let's see what happens when the axis of revolution is below the region. So when we rotate this red rectangle, I'll have a gap here, another gap here, and the rectangle's rotated this way. So my washer looks like this. And this distance is still root x. This red rectangle is still root x. This is 2. The outer radius is the distance from the center of the washer to the top. So this is the outer radius. The inner radius is the distance from the center of the washer to this piece. So can you find little r and big R? Take a minute and think about that. How would you represent little r and big R here? Well, big R is this piece, the red piece, plus 2, right? Does everyone see that? It's the red piece. Oh, wait, let me just put that in yellow. The red piece, oh, maybe I should put that in red, plus 2. That's the big radius. So that would be root x plus 2 squared. That's the outer radius. The inner radius is always 2, because notice that the distance from the bottom of the rectangle to the axis of revolution will always be 2. So we subtract 2 squared. And that would be the integral for that piece. Now the question is, how can we do this with the least amount of work? Well, I thought about this for years. And I finally came up with a formula that would work. And it goes like this. Okay, listen very carefully. The shortcut is the following. Okay, and I'm going to write it here on the page, and I'll summarize on the next page. The generic formula is, okay, and I'll put this in yellow. Pi on the outside, always. The limits of integration, whether they're in terms of x or y, depending on the situation. Now, we start with this. It's the axis of revolution minus the function furthest from the axis of revolution I'll put AOR squared. Okay, minus the axis of revolution minus the function closer to the axis of revolution squared. And whether it's dx or dy, that's up to you, depending on a vertical or horizontal rectangle. So let me explain how we do this. For D, the axis of revolution is 3, right? But the function that is closest or furthest away from the axis of revolution is the x-axis, which has the equation y equals 0. So it's 3 minus 0 squared, which is just 3 squared. And in the second piece, it's the axis of revolution 3, And the function closest to the axis of revolution is the blue function root x, and we square it. So it works for D. Let's look at E. The axis of revolution 5 minus the curve furthest from the axis of revolution is still the x-axis, which is y equals 0. So it's 5 minus 0 squared, which is just 5 squared, minus the axis of revolution 5 minus the function closer to the axis of revolution, which is the blue curve, root x squared. Now let's look at F. All right. Now this one works the same way. It's the axis of revolution, which is -2, minus the curve furthest away from the axis of revolution. Well, because y equals -2 is below, the curve furthest away is root x squared minus the axis of revolution, which is -2, minus the curve closest to the axis of revolution, which is just the x-axis, y equals 0 squared. Now, these two are the same. Why? Because if we take out a -1, -1 squared is 1. So these two are the exact same integrand. But that's a nice formula that will always work. Always work. But you cannot do this unless we sketch the area of the region and the axis of revolution to see which one is closer and which one's further away. So let's summarize on the next page. All right. So today we looked at the volume of a solid of revolution using the washer or disk method when we rotate the area bounded between two curves about the axis of revolution that is parallel to the x or y axis. The first thing we have to do is sketch the area of the region. Okay, this is very important. Label the functions, intersection points, and your x and y axes. Right? Because we can't tell which one is the axis of revolution and which one's the x or y axis unless we label them clearly. Okay, 2. And, all right, so we found the intersection points, and then we decide which rectangle spans the area. So that's either a vertical rectangle which we look for the top and bottom, and we integrate with respect to x. And then horizontal rectangle, and here we look at right and left, and we integrate with respect to y. So remember, with the washer method, to get the washer, the rectangle has to be perpendicular to the axis of revolution. If it's not, we use another method called the shell method, and we will discuss that next time. Okay, so again, if the axis is horizontal, then the rectangle we use is vertical, like we did in all the other problems, and we integrate with respect to x. So everything has to be in terms of x. If the axis of revolution is vertical, The rectangle we have to use is horizontal to get that washer look. And we integrate with respect to y. Okay, and this should be 2x. That's what I get when I rush. Okay. All right. And the generic formula. Okay, this took me a long time to figure out. I've been teaching this unit for so many years without this formula, and I don't know how I did it. But this formula is so helpful. Okay, so the volume is equal to pi on the outside, whatever your limits of integration are, x or y, axis of revolution minus the function further away, and we square that. Okay, so there's a lot of squaring on this and a lot of subtracting. Minus the axis of revolution, whatever the number is. That's what I mean by axis of revolution. This is a number. Minus the function closer to the axis of revolution. And when I say further away from the axis of revolution, okay? So it's all relative to the axis of revolution, squared. So we've got subtraction in the parentheses. We square and then subtract those two. And this is the outer radius squared. This is the inner radius squared. And depending on whether it's dx or dy. And that has been really very useful for the past few years I've been teaching it. So I hope you'll enjoy that. Let's try a problem by ourselves. Now we're going to look at the same region since we've been talking about it. The region bounded by y equals root x, x equals 9, and the x-axis again. But this time, we're going to rotate around vertical axis of revolution. So in the first one, we have x equals 9. So let's draw that axis of revolution. That's right on the boundary of the region. So we go around this way. In the second one, we go 1 to the right of x equals 9. So that's x equals 10. And then in the last one, we go to the left of the region, x equals negative 2. Okay, and we go around this way. Now, in order to create a washer, the rectangle has to be the opposite orientation of the axis of revolution. So since these axes are all vertical, the rectangle we must use is horizontal. So we draw a horizontal rectangle in the region as if we're finding its area. Now, when we rotate these rectangles, notice that this rectangle is sitting on the axis of revolution, so we'll get a disk. The next rectangle, well, there's a gap here, so there's a gap here, and we'll get a washer. And then in the last one, the gap is to the left of the region, right? So that we'll have a gap again on this side because of the symmetry, and our rectangle would be here. Okay, I'm trying to get my washers just right, but it's a little hard. But again, that's all we need. We just need one washer. We don't really care what the solid looks like. This is enough to help us set up our integral. So since we use horizontal rectangles, okay, let's just get the white marker here. Oh, it's not working. Horizontal rectangles. In each of these, we integrate with respect to y, which means that our functions have to be expressed in terms of y, and our limits of integration have to be in terms of y. So let's figure out what that is. We still have a pi on the outside. what would be the y limits of integration? Well, if you recall, this point here was 9, 3. So we use the 9 for the x limit of integration. We're going to use the 3 as the y limit of integration because our solid is bounded by these two horizontal lines in each figure. Okay, so the integral is from 0 to 3 in every one of these. Now, the next thing we have to do is we have to solve for x. So let's do that. So when x is equal to root y, I'm sorry, I did this backwards. Oh my goodness. Okay, let me do it again. Let's try it again. When y is equal to root x, x is equal to y squared. So this is what we'll be using for our horizontal distance, which is the x coordinate. So in each one of the integrals, we're going to be using a y squared. So let's try it. All right, pause the video and set up the integral the way we discussed. Everything relative to the axis of revolution. Okay, so we start. Axis of revolution, which is 9, minus the curve furthest away from the axis of revolution. Well, that is y equals root x, or x equals y squared. And we square that. Don't forget to square the radius. This represents the outer radius minus the inner radius squared. Well, the inner radius is the axis of revolution, which is 9, minus the curve closest to the axis of revolution. Well, if you look at this horizontal rectangle, the right and left ones, the right side and the left side, well, the left side touches the square root function. The right side touches the axis of revolution. So that's just x equals 9. So this would be our integral. Or just 0 squared, which we could just ignore. And remember, with the disk method, the inner radius is 0. So we could have ignored that. The inner radius is 0. Okay, but it works either way. All right, let's look at the next one. So the next one would be the axis of revolution. Okay, so I could even set this up. Minus squared, right? Okay, now the curve furthest away from the axis of revolution is still the square root function, so I'll put y squared. Oh, I could move this down a little. Let me erase that. Minus the axis of revolution, which is 10, minus the curve closest to the axis of revolution. Well, the curve closest to the axis of revolution is x equals 9, because that region bounds the area. So that's 9 squared. And dy. So remember, this distance here will always be 1. That vertical line to the axis of revolution is always 1 away, which is usually difficult to find otherwise, but I'll leave that up to you. Now let's take a look at the last one. Here, x equals -2 is to the left of the area of our shaded blue region. So notice that the horizontal rectangle that's drawn in the representative horizontal rectangle that's drawn, the washer actually goes this way. And again, the inner radius of this washer is this distance. Let me just do this in green so you could see it. This is the inner radius. And the outer radius of the washer is this distance. right? The distance from the right function, the function furthest away to the axis of revolution. And remember, it's all in x equals. So if we set up the integral, we have the axis of revolution, which is -2, minus the function furthest away from the axis of revolution. So that's going to be the right or left function that bounds the rectangle. In this case, it's the right side, which is x equals 9 squared, minus the axis of revolution, minus the function closer to the axis of revolution, which is the left function, and that's the square root function, which we call y squared, but we square that. And if you look at this carefully, this outer radius, this distance to here, will always be 11, no matter where the washer is, or the horizontal rectangle is. That will always be 11. So whether we square -11 or +11, it's still 121. And then finally, to get the inner radius, we have to take into account this horizontal distance, minus the -2. So we could even represent that as y squared plus 2 squared, which, of course, would take care of the second piece. So actually, when you think about it, the y squared would be this distance here, this distance, and the 2 is here. So the distance from here to here is 2. The distance from here to here is the y squared. And when we add them, we get the inner radius. Okay, because my washer wasn't drawn really precisely, it should be that way. Okay, so that takes care of that integral. All right, let's try one more before I show you the animations. Okay, so this one is good practice. I just like to set up the integrals for these. Region R is bounded by the parabola y equals x squared plus 1, x equals 0, and y equals 2. Find the volume of the solid of revolution when R is revolved about these lines. Okay, so first, again, it's important to sketch these. So I'm going to sketch these 3 times. Okay, so I sketched part of the parabola. I just sketched the region bounded by y equals 2, the y-axis, x equals 0, and the parabola. It looks like this. And when y is 2, x is 1. So the intersection point here is 1, 2. 1, 2. And this is y equals x squared plus 1. Okay, now let's sketch the axis of revolution. Y equals 3 is above this curve. Y equals -1 is below this curve. And x equals -1 is to the left of this curve. 1. This is y equals -1. So we're going around this way, around that way, and around this way. Now, the first thing is to determine what rectangle we must use to get a washer. So for the horizontal axis of revolution, we need a vertical. And for the vertical axis of revolution, we need a horizontal. Okay. Now, we could draw the washer if you wish, so you could see it. And in this one, we go down. Okay, I have to go into the other diagram, but I think you see that the washer would go down this way. Okay, I'll try to correct that later. And for this one, we go to the left, and the washer goes this way. So I'm just going to try to correct the second one. Okay, I think that's better. So now when we rotate this vertical rectangle about y equals -1, we've got a gap here, another gap here, and a rectangle would go down this way. So, oh, and it's not very symmetrical. Hold on, let me just try to get this. Because again, this is, so whatever is here should be down here. So this washer is still going to collide into the other diagram, but that's okay. So this is the empty circle, and this is the outer circle here. But I think we get the idea. All right, so now, for the first two, we'll integrate with respect to x. Okay, let's just make a little note. And for the last one, with respect to y. So immediately we could start putting our pi on the outside. Our limits of integration. The x limits of integration would be from x equals 0 to x equals 1. But the y limits of integration would be from, let's see now, y equals, well, this point here is 0, 1. So it would be from y equals 1 to y equals 2. Because note that if this is 0, 1, and this is y equals 2, then we see that our region is bounded by the lines y equals 1 and y equals 2. So those would be the limits of integration. All right, let's start. Now, again, for the last one, we have to solve for x. So if y equals x squared plus 1, we subtract 1. And here we would have to say the positive or negative square root of y minus 1. But of course, it's on the positive side, so we'll just take the positive square root. Okay. Now let's set up our integrals. So for the first one, we take the x of revolution and subtract the function furthest away. Well, that's the parabola. And this needs to be put in parentheses because we're subtracting it, squared, minus the x of revolution minus the function closest to the x of revolution. Well, that's the line y equals 2, squared. And again, this distance, the inner radius will always be 1. All right, now for the next one, we have the x of revolution minus the curve furthest away from the x of revolution, and that's the line y equals 2 minus the x of revolution minus the curve closest, and that's the parabola. And again, we need parentheses there, squared. Okay, don't forget your dx and put this in brackets. So let's see what this is saying. So that the distance, the outer radius, is always 3 away. And it makes sense because this distance from the x of revolution to the x-axis is 1. And this distance is 2. So that the outer radius will always be 3. Okay, and then for the last one, again, we have to put it in y. So it would be the x of revolution, which is -1, minus the curve furthest away from the x of revolution. And the curve furthest away is the parabola, which would be the square root of y minus 1. Squared minus the x of revolution minus the curve closest to the x of revolution. And that is the y-axis, which is x equals 0 squared dy. And if we look at that carefully, notice that this inner radius will always be 1. Will always be 1. No matter where our vertical or horizontal rectangle is drawn, it will always be 1. Okay, so that takes care of volumes of solids of revolution using the washer method about other axes. Let me show you 2 animations. This is a geometer sketchpad animation of revolving the area bounded by y equals the square root of x from x equals a, which I tried to make it from 0 to x equals b. And notice that we're revolving this area bounded by the square root function, the x-axis, x equals a and x equals b, about this horizontal line, y equals -2. Here's our representative vertical rectangle that we would use to get the area. Now let's revolve this region together with the rectangle and watch what happens to the rectangle. So we see that that rectangle becomes a washer. And notice that the solid that's being formed has a hollow cylinder in the middle. There's a hollow cylinder in the middle, but the part where the washer is shaded is the part where the solid is for this figure. So if we sweep the disc and washer, we see where the solid part of this three-dimensional figure is. Notice that wherever the washer is sweeping, that's the solid part. There's a hollow cylinder in the middle of this solid. Okay. Now let's reset this, and we're going to move the axis of revolution above the region. So I'm going to make it x equals 5. And I'm going to move this down because now we're going to be rotating above. So let's see if we could do this. Now, if we start revolving, okay, let's try this. Oh, maybe I should start this over. Let me just try it again. I'm going to reset. Okay, so we're going to revolve. Okay, let's reset. We're going to revolve the area of this region about the line y equals, well, something like 5. Okay, now let's revolve it so we could see it. And notice that the area is being flipped up. And the vertical rectangle is still a washer, becomes a washer. And it's very important to note that the axis of revolution in all of the figures go right through the middle of the solid, whatever it may look like. And this solid that's being formed has this hollow piece in the middle. This part's hollow. The solid part is here, formed when we revolve the area bounded by y equals the square root of x from x equals a to b about this line. Now, if we sweep this washer, we see that that piece would be the solid part of the three-dimensional figure. But again, this piece, this funnel in the middle, is hollow. Okay, so that takes care of the animation of volume of solid of revolution formed by revolving around another line other than the x-axis. Here is a GeoGebra program created by Steve Phelps. And if you notice here, this red region is the area that's being rotated about this blue horizontal line, and it looks like the equation is y equals 6. So let's just review how we would set up an integral for that. So we would do 6 minus the formula for the function furthest away from the axis of revolution, which would be this bottom curve, because this bottom curve is further away from the axis of revolution. So it would be 6 minus whatever this curve is squared minus, and then in parentheses, 6 minus whatever the equation is for the curve closer to the axis of revolution squared. And of course, from x equals a to b, whatever those are. But what I want wanted to show you is what the solid looks like, even though we don't really have to worry about that. Kind of amazing that we have the knowledge to do this. And I thought I wanted to share this with you. So the solid, when we rotate that region about that line, y equals 6, notice that there is a hole in the middle. This was created by the inner part of the washer that's hollow. But this outer part is, is the washer, all the washers that we use to cut through the solid to approximate the volume of the solid of revolution. And I like the 3D rendition here. Just rotate this solid and you can see from different angles what it looks like. It almost looks like garlic, but it's cut out in the middle. Yeah, I think this is amazing. But notice that we're rotating this red region about the line, and whatever's in red forms the solid that we see going through here. Get it to go the other way. Right. So we appreciate the solid part and the hollow part. And that axis of revolution goes right through the middle of the solid. So I thought that you should see this 3D rendition. It's beautiful. Okay, that takes care of volumes
I
of
hope you
solids of
enjoyed the
revolution.
videos, and I wish you all a wonderful day. Okay, take care now. Bye.